Lesson: Training neural networks, backpropagation and optimization techniques. Training neural networks effectively involves mastering the concepts of backpropagation and optimization techniques, which are critical components in developing robust AI models. Backpropagation is the cornerstone of neural network training, allowing the model to learn from errors by adjusting weights to minimize the loss function, which quantifies the disparity between predicted and actual outcomes. This iterative process ensures that the model's predictions become increasingly accurate over time. Optimization techniques, on the other hand, are algorithms designed to enhance the efficiency and speed of the training process, ensuring the neural network converges to an optimal solution. Backpropagation works by propagating the error backward through the network. It involves two main steps: forward pass and backward pass. In the forward pass, the input data is fed through the network, layer by layer, to generate an output. The loss function then calculates the error between this output and the actual target. In the backward pass, this error is propagated back through the network, updating the weights using the gradient descent algorithm. This process is repeated for multiple iterations or epochs until the model reaches the desired level of accuracy. Gradient descent is a fundamental optimization algorithm used in backpropagation. It works by iteratively adjusting the weights in the direction that reduces the loss function. However, simple gradient descent can be slow and may get stuck in local minima, which are points where the loss function is lower than the surrounding areas, but not the lowest possible. To address these challenges, advanced optimization algorithms have been developed, such as stochastic gradient descent, which updates the weights using a subset of the data, known as a mini-batch, rather than the entire dataset. This approach not only speeds up the training process, but also introduces a degree of randomness that helps escape local minima. Further enhancements to SGD include the introduction of momentum and adaptive learning rate methods. Momentum helps accelerate SGD by using the concept of velocity, which allows the algorithm to build up speed in directions with consistent gradients, helping to overcome local minima and reach convergence faster. The RMS-prop and ATOM optimizers are examples of adaptive learning rate techniques that adjust the learning rate during training. RMS-prop divides the learning rate by an exponentially decaying average of squared gradients, which helps in dealing with the vanishing gradient problem often encountered in deep networks. ATOM, or adaptive moment estimation, combines the advantages of both RMS-prop and momentum, providing an efficient and effective optimization strategy. Implementing these techniques in practice requires familiarity with popular deep learning frameworks such as TensorFlow and PyTorch. These frameworks offer pre-built functions for backpropagation and optimization, enabling practitioners to focus on model design and experimentation. For instance, TensorFlow's Keras API simplifies the model training process by allowing users to easily specify the optimizer, loss function, and metrics during model compilation. PyTorch, on the other hand, provides dynamic computation graphs, which offer greater flexibility in model building and debugging, making it a preferred choice for research-oriented tasks. Consider a real-world application such as image classification, where a neural network is trained to categorize images into predefined classes. Using a dataset like CIFAR-10, which consists of 60,000 32 by 32 color images in 10 classes, one can employ a convolutional neural network architecture. During training, backpropagation adjusts the weights of the convolutional layers based on the error computed from the classification results. By incorporating optimization techniques like ATOM, the model can achieve high accuracy in recognizing objects in images with minimal manual intervention. To illustrate the impact of these techniques, consider a case study on autonomous vehicles. Training a neural network for object detection and recognition in self-driving cars involves processing vast amounts of data from sensors and cameras. Backpropagation enables the model to learn from mistakes by refining its predictions continuously. Optimization techniques ensure the model can process data in real time, a critical requirement for safety and performance in autonomous driving. Companies like Tesla and Waymo leverage these techniques to improve the accuracy and reliability of their AI systems, resulting in safer autonomous vehicles. Despite the effectiveness of backpropagation and optimization techniques, challenges remain. One significant issue is the vanishing gradient problem, where gradients become too small for effective learning in deep networks. Techniques such as layer normalization and skip connections, as seen in ResNet architectures, have been developed to mitigate this problem by facilitating better gradient flow through the network. Another challenge is the need for large labeled datasets, which can be resource-intensive to produce. Transfer learning offers a solution by leveraging pre-trained models on similar tasks, reducing the need for extensive labeled data and computation resources. In conclusion, understanding and applying backpropagation and optimization techniques are essential for training effective neural networks. These methods form the backbone of modern AI applications, enabling models to learn from data and improve over time. By utilizing frameworks like TensorFlow and PyTorch, practitioners can implement these techniques efficiently, addressing real-world challenges in various domains. As neural network architectures continue to evolve, staying abreast of advancements in backpropagation and optimization will be crucial for AI professionals seeking to enhance their models' performance and reliability.